Good afternoon, everybody. Or I guess it might be good morning for some of y'all. This is our first official sort of recorded lecture. Just a little bit of like housekeeping and, just as far as understanding my place in this. This is actually my first time going through and trying to figure out how to do these lectures effectively to give you information, but also not being redundant. So if you can give me, I guess you would say like not positive feedback, constructive feedback regarding like what works for you, what doesn't work for you, how can we spend this time in a more useful way, that would be, ideal for me. But we'll start with this and we can iterate as we move through the semester. But yeah, be as clear as you can and just let me know what works for you. But anyways, good morning. Today we will be diving into crystallographic points, a fundamental concept in understanding the arrangement of atoms in a crystalline material. This topic is crucial for fields like material science, metallurgy, semiconductor physics, right? All fields which touch things that you are interested in this class. And so this is square one. Journey of 1,000 miles begins with one step. We know how atoms are arranged and how their arrangements impact material properties. We talked a little bit about that last week from like a higher level concept with specifically metals and ceramics. However, in this lecture, I want you to sort of think about going 1 foot deeper and think about how we are going to define crystallographic points in a more sort of rigorous academic way. And so we have 3 goals for today. Let me just scroll down to my notes. 3 goals. So number 1, I want you to think about how are we defining crystallographic points. Right, so we're thinking about what is the overall definition of these and what is the nomenclature, so the words, the terms, the variables that we're using to sort of create this box. Number 2, understanding lattice parameters. I swear my handwriting is going to get better. I swear it is as we go through the semester. But yeah, think about those lattice parameters, and then the 7 crystal structures that those parameters help inform. And you can find that actually on table 3.6 in your book. Sometimes when they show you a table, it actually is really, really important. This is one of those important tables. And then last but not least, recognize why these concepts matter. So that's, something I want you to be reflecting on as we move through any course, right? Is why does this matter? How does this connect to other domains that I've sort of studied? And what does that mean as we sort of move forward and think about it critically? So with that, we will move to the next point, which is what are the crystallographic points? So crystal materials have certain properties. Number 1, they are regular, they are repeating, and they, as in the atomic structures, repeat their arrangements, right? And that is what is called a lattice. So if it's regular and it's repeating, it is a crystal, or it can be classified as a crystal lattice. So each atom in this lattice, right, atoms have specific locations, which we can use to describe, we can describe using a coordinate system. And so this is thinking about, okay, we have this X, Y, Z Cartesian coordinate system, right? So we're thinking about, in terms of 3 dimensions, how can we reference a specific position within the unit cell utilizing this X, Y, Z arrangement, right? And so we describe this as It's all going to be relative to the unit cell. And so what this means is because it is relative to the unit cell, it's going to be XYZ, right? Coordinates all on a 0 to 1 unit cell, right? So the range will be 0 to 1 for all of those values, whether they are at, depending on where they are within that specific cell, 0 being min, 1 being the max. Let's give you some examples though. And so right here we have our, in this case, we're thinking about XYZ, but this is, they're using ABC, same thing, right? We can see side A is parallel with X, boop, boop. Side B is parallel with Y, and then side C is parallel with Z, right? This is what you'll see, in any sort of other, you'll see this pop up in physics as well, or sometimes like linear algebra, right? But when we're thinking about this specifically, if we want to give an example, with this specific, let's say this is a unit cell here. If we want to think about 0.001, right? And like, let's say the origin is right here. It's all coming from the back, right? This would be let's just give you little dots out here. 0, 0, 0, right? Because it is, on all of those scales at the origin. If we wanted to define something like 0.5, 0.5, 0.5, we'll use red. So you would go, okay, well, where is the intersection of 0.5? Right here, right on the z-axis, right here on the, what do you call it? The y-axis, and then right here on the what do you call it, x-axis. And so we just bump this across, right, when we think about where it is. And it should be, sorry, that was a little confusing, but essentially you get the idea. This is in the middle, right? So 0.5, 0.5, 0.5 should be directly in the middle. So we can also get there by drawing diagonals from every single corner, right? And we'll get the middle. So that would be an example of 0.5, 0.5, 0.5. There we go. So something to also note, and this is some carryover from last lecture, is thinking about the different crystal structures have unique arrangements. And so we were talking about some crystal structures last week, specifically BCC, FCC, right? And so some of the things to just sort of think about and note, make connections on, right? So different crystal structures have, what do you call it, unique arrangements. So number one, simple cube, right? You will find atoms only at the corners, right? So you're looking at something in the range of boop, 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 boop. We'll leave more space next time. Boop, boop. So you'll find only at the corners will you have atoms, right? If we're thinking about something that's a little bit more complicated, like the body-centered cubic, BCC, we're going to find one additional atom, right, at the center. And so if we think about our cubic structure here, boop, 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 boop. We have a 0.5. Let's go back. 0.5, 0.5 added on top of the simple cube. So you have one center. Here, we can make those different colors. Greens. Right, and this is your BCC. And then last but not least, we have our FCC, right, which is our face-centered cube. So there's an atoms at the center of each face. So if we draw it out, it's going to look something like this. Boop. Boop. Sorry, I'm booping right now. There you go. So if we did it in red, you would have it at atoms at the center of each face. Maybe I'll just make this one. In the future, we'll do like, we'll get rid of these. So we have, sorry. Right, and then instead of a solid one, we'll do that. There you go. So you get that idea. I guess we are missing one on the front here too. And that should be erased because we can't actually see these. We'll have to figure out the verbiage and the actual, how do we want to describe this? Or how do we want to illustrate this? Because if we're working in 3 dimensions, it could get a little bit confusing. But yeah, so the example here is, you're looking at no center point, and then you also have points at, let's just say, depending on the face, you have something that's variable, and then you have it could be something like 0.5, 0.5, 0, right? So you're looking at 0.5, 0.50 as your FCC. So now that we understand how those atoms work and how they're positioned, let's talk about how we describe the overall shape of the unit cell. This is where the lattice parameter comes in. And so if we think about the lattice parameters, that can be found, like I said before, textbook 3.6, table 3.6. These parameters include the edge length, so ABC, which is the axial relationship. And then we think about the interaxial relationships, which are the angles. So this will be alpha, beta, gamma. And so if we look at cubic, hexagonal, tetraagonal, rhomboidahedral, orthorhombic, monoclinic, and triclinic, you can see how all of the different relationships between the axial and interaxial affect the overall shape of or structure of the unit cell geometry. So if we're thinking about like real world examples, FCC, which is a cube, right? This could be aluminum, copper, right? And this could be like, because it is this shape, it's ductile, it's a good conductor, it tessellates nicely into other sort of crystalline structures. If you're thinking about this hexagonal, we're thinking about magnesium graphite. It's more it has a different sort of like a stiffness, right? It's less ductile. It's a good insulator, and because of the, what do you call it, ways that the crystals are structured relative to each other. So the key takeaway here is that cells packaged different way, or crystals packaged different ways. So we're thinking about density. We're thinking about, can have different mechanical properties and material behaviors. So delta density. Yeah, there we go. So when we think about, why do crystallographic points and lattice parameters matter, we need to know these attributes because at the end of the day, they help us understand and predict how materials will react in specific situations, right? So FCC metals like aluminum have slip planes, making them more ductile, whereas BCC metals like steel have fewer slip planes, meaning that they are stronger and less ductile, right? And so we also need to understand, how we can analyze their, their defects and diffusions. And so when we think about, predicting what could possibly go wrong or like failure points for specific materials, we can think about like vacancies, so where there are missing atoms or interstitial extra atoms, right, within specific lattice planes. So opportunities for these types of discrepancies can affect the material performance. And then last but not least, diffusion rates depend on the lattice structure, which are important for alloys and semiconductors. Which, thinking about how do we optimize materials for cost-benefit analysis, things like that. Silicon is like a really good example when we think about like semiconductors, because it is widely used in chips, because the crystal structure allows for controlled doping and electron movement. All in all, the atomic structure determines the mechanical, electrical, thermal properties, which is why engineers need to understand the crystallographic concepts. So, to wrap things up, crystallographic points describe atomic positions inside the unit cells using fractional coordinates. Lattice parameters are the 7 crystal systems that determine the material properties. Make sure that you're familiar with those. And then these principles are crucial for material selection, processing, and engineering applications. And so just being able to sort of usefully interact with this, and we'll move on to calculations, as we sort of move forward. But, get your head around the big pictures things so that we can, dive a little bit deeper. As sort of a bonus question, I want you to sort of think about that, this knowledge isn't just theoretical. It's the foundation for everything from like stronger aircraft materials, faster computer chips. And so thinking about like, as you move forward, right, really having a critical lens of like where the intersection of this with things that you're going to be building, where those exist. And so, that's all I have for you today.